Good morning, good afternoon, good evening to everyone joining us from different parts of the world. On behalf of Canada-Nepal Forum for Research, CANE4, I warmly welcome you in this today's seminar. My name is Bhanu Bhakta Acharya. I am the president of the CANE4. I'll be hosting today's session and moderating the discussion following the keynote presentation. Before we begin, I would like to inform you that our originally scheduled program host, Dr. Dinesh Gajwal, is unwell and not able to host this event today. We wish him a speedy recovery, and I'm expecting he's also joining as a part of the audience here. And I'm grateful for this opportunity to step in and facilitate this important scholarly exchange. The Canada-Nepal Forum for Research, CANE4, is a non-profit, volunteer-driven academic platform committed to promoting research collaboration, knowledge exchange, and interdisciplinary dialogue between scholars in Canada, Nepal, and beyond. As a part of this mission, CANE4 regularly organizes annual conferences. We have started organizing webinar series and other academic forums that bring together researchers from diverse disciplines to address contemporary scientific, social, and policy-driven challenges. Today's webinar is a part of this ongoing series, and it focuses on topic of growing importance in rapidly urbanizing societies, urban soundscape, and noise modeling. Actually, I'm also not very much familiar on this topic, but hopefully this webinar will make a very aware of this idea, and this is something very contested, new, and emerging topic of discussion. The title of today's webinar is Numerical Modeling of High-Resolution Soundscape in a Complex Urban Environment. Rapid urban growth has intensified noise pollution in cities worldwide, particularly due to transportation system such as road traffic and railways. These sound sources do not travel in simple ways. They interact with buildings, streets, and open spaces, producing complex acoustic environment that directly affect public health, urban livability, and planning decisions. Today's session explores how high-resolution numerical modeling, especially using the spectral-element method, can help us better understand sound propagation in dense urban setting. The work presented today offers not only scientific insights, but also practical implications for urban planning, noise mitigation, and evidence-based policymaking. It is now my great pleasure to introduce our keynote speaker, Dr. Homnath Garthi. He's an assistant professor and digital earth scientist in the Department of Geological Sciences and Geological Engineering at Queen's University, Kingston, Canada. Dr. Garthi's research lies at the intersection of computational modeling, geophysics, and digital earth science. His work is particularly known for advancing high-resolution numerical simulation to better understand complex physical processes, including wave propagation in challenging environments. In today's talk, Dr. Garthi will present a high-resolution digital soundscape of a complex urban environment developed using the spectral-element method. His modeling captures detailed acoustic behaviors such as reflection, scattering, and localized amplifications, offering a physically grounded framework for understanding how sound behaves in real urban setting. We are delighted to have Dr. Garthi with us today, and we look forward to learning from his research and insights. Before handing over the floor to our keynote speaker, let me briefly outline the program. First, keynote presentation by Dr. Homnath Garthi to 45 minutes approximately. And the question and answer session will be moderated by me after the presentation. And we'll close by wrapping up. And a few housekeeping notes here. All the participants are welcome to post your question in the Zoom chat at any time during the talk, because this is a very new contest and maybe unfamiliar talk to many of us, including me. So I also can ask question myself. And I will moderate the discussion and pose the question to the speaker during the Q&A session. So with that, it's my pleasure to invite Dr. Homnath Garthi to begin his keynote presentation. Dr. Garthi, the virtual floor is yours. Thank you.
Thank you very much, Dr. Acharya, for introduction. And good morning, everyone, and thank you very much for joining the webinar. So first, let me share my screen. Is it visible now?
Yes. Yes.
So today I'll talk about the numerical modeling of high-resolution soundscape in complex tone. So this is my collaborator, Pedro Lapietra Garcia. So was my graduate student. Now he is the technical project lead at Sandra Geophysics. So he is currently in vacation in Brazil. I'm not sure whether he will join later. So this is the outline of my talk. First, I will briefly give the background of my RO, and then I will briefly touch upon the numerical modeling. Why is it important? And then I will describe how we can compute the soundscape in this environment with example in the city of Kingston, where I currently reside. And then finally, I will summarize and list some of the future interesting work. So the noise pollution, we have everybody has heard about this, but it seems to have less attention than the other counterparts. For example, water pollution or air pollution. But with the, for example, rapid urbanization, it has become actually important. And even without this, the noise pollution is actually the very critical in our day-to-day life. So, for example, if we these days, due to the rapid urbanization, infrastructures they usually tend to concentrate, and sometimes the people focus on the vertical development instead of the kind of the spectral distribution. So that actually also increases intensifies the noise pollution. And the prolonged exposure of noise pollution, actually, they are already reported to have the physical and the effect on mental well-being. That's why if we have the kind of the detailed, realistic or scientific soundscape, then we can actually have the policy and planning that would help us to mitigate this kind of noise pollution. So that's why the soundscape is very important. But the question is, what is soundscape? So let me start with the familiar word that we have already heard about, landscape. So landscape is basically related to our sight. So what we see in front of us is basically the landscape. So this is actually the beautiful landscape from Nepal. Actually, this is my village. So let me set my pointer here. Yeah, so this my village is somewhere here, and this is my high school. So as you can see that this picture, my village and high school seems to be very close, but actually there is a small river between those two small mountains, and it used to take about 2 hours to go to my school. So I used to go to my high school walking 2 hours every day. So this is very beautiful landscape, right? So it captures the landform from the trend for the natural and features. Right? So this is the landscape. So on the other hand, so the soundscape looks something similar. So this is the soundscape that I will be talking about. So this is the computed soundscape in city of Kingston. So this is the hearing, right? So instead of seeing, we are hearing something. So if you go to certain place, you can hear the different level of sound. And we can actually map and plot that sound level, and which is the soundscape. And similar to landscape, it is actually acoustic environment or the sound environment. And it actually captures the variation of the sound or the noise level in the spectral projection. And this also captures both natural and anthropogenic sounds. So, because this computing or estimating the soundscape is not an easy task, so that's why we must resort to the numerical model. So that's why I know most of you may be already expert in numerical modeling, but I just wanted to the interesting about the very simple introduction to the numerical model. So what is a numerical model? So this is actually the problem from our ancestor. So if you look at the history, so some of the old structure are actually built circular. It looks like our ancestor were kind of they have the affinity to the circular structure. If you see our old coins, for example, these days our coins as well are actually circular. But at that time, they didn't know how to compute the perimeter of the circular structure. What they have is just the simple stick. They didn't have the formula that, for example, 2 pi r is the circumference that we know, but they didn't know at the time. And they didn't have the complicated instrument to measure this perimeter. So I'll pose you the simple questions. Of course, you don't have to answer because all you are admitted, but you can think in your brain. Right? So just using this stick, how can we measure the perimeter in the circle, which is of course the curve, right? Not the stick. So at a glance, this is a very complex challenge, right? Because you have the each fit ruler that you need to use to measure this curvilinear structure's perimeter. But how they measure at that time is just break that circle into the simple pieces like this, right? So instead of just measuring that curvilinear, which is impossible by using that straight ruler or stick, they just broke that circular structure or circular perimeter into the number of straight pieces. And then suddenly, those stress piece can actually be measured by this stick, right? So the basic principle here is that the perimeter is basically the sum of those segments. So the basic goal or basic idea or the object of this idea is that we can actually solve any complex problem breaking into the small and simple problem. This is the main idea of numerical modeling. And interestingly, this principle actually also applies to our real life problem as well. So if you have any complex problem, you can simply break down that problem into the simple problem, and suddenly you are able to solve the problem. So this numerical computation is actually used in daily life without knowing what the numerical modeling is, for example, right? So this is the beautiful picture I took from my garage this summer. So my wife is the avid gardener, so she planted the sunflower. So you see the very vivid picture here. So even you can see that bug enjoying this flower. So it's very complicated picture. But if you see this picture in detail, so basically it has been decomposed into the number of square cell, and each square cell is basically just single color. Right? So it is amazing. So basically defining the single uniform color in each cell, we are able to represent or visualize this complex and vivid picture. And this picture is, for example, represented by about 12 million pixels. So that means your smartphone is basically internally computing for you. It's using the numerical modeling inside. So that's why numerical modeling is very important. So there's this slide. I always show this in my class, which is very important. I always pull out the recent data, and it basically shows the real importance of the computing or the numerical modeling. Why is it really important? So there is a non-profit organization called Top 500, which actually rank the supercomputers around the world. So it basically measures the performance of each supercomputer in terms of the flops. So that is the floating point operation per second. So basically, if you add two number or divide two number or subtract two number, that would be the one floating point. So here in the graph, horizontally, you will see the year. It started about 1992 up to this. So it's continually going. So in the vertical scale, you will see the units of the performance. So you will see the three different graphs. So one will be the 500th most powerful computer right now in the world. And the triangular will be the number one. And the green dot will be the summation of the top 500 leaders. So this is the evolution of that computing performance in the world. For example, around 1995, the top supercomputer had the performance about 100 gigaflop, but now it exceeded the exascale performance. So that is simply unbelievable. So it is the rapid growth of the computing environment. If we see the trend line of those curve, it's that line in logarithmic. So that means the computing power is exponentially growing, similar to Moore's law, which we used to learn, for example, computer science. Right. So what is interesting here is that, for example, this region is the where our current smartphones lie. So the high in smartphone have about 4 teraflop, or some even more than that performance. So what does that mean? Is that in 2000, so that means just 25 years ago, our current smartphone was the top supercomputer in the world. So that means basically you are right now holding the number one supercomputer of 2000 in your pocket. So that is simply unbelievable. So this computing power has rapidly evolved over time. So I'll show you some couple of snapshots. So that is those you see the type triangle. So that is the position of the top supercomputer in 2002 to 2005. So that was called the Earth simulator. So that is that supercomputer at the time, which was in Japan. So that is the first time that the scientists were able to simulate the entire Earth for the seismic wave propagation. That's why it is called the Earth simulator, and it was primarily built that purpose. And you see these white blocks there. These were actually the refrigerator, because this computer, when they run the big problem, when they are computing, they generate a lot of heat, and we need to cool them down. So that's why they have to have this dedicated refrigerator. And you see those blocks, gray blocks there, those were the parallel computers which constituted that supercomputer, world first Earth simulator in Japan. And that hold the position of the top supercomputers for several years. And then that is another interesting position there. So that is the top supercomputer around 2020, and for a few years. So that was again in Japan. Right now, that is the 7th top supercomputer in the world, just in 5 years. And I listed that here because I have the very interesting connection with this. So you see the symbol on that computer. So that is actually the Fugaku. That is the Fugaku word. So that means the number one, or the Ichiban in Japanese language. And that is the mountain behind there is the Mount Fuji. So Japanese people, they revere this Mount Fuji as some deity. And I have actually been to the top of this mountain when I was in University of Tokyo during my master's degree. So that is the reason why I listed this. And it used to be the top supercomputer just 5 years ago, but now it is the 7th in the world. But Japanese government, they just budgeted another supercomputer. They call it Fugaku Next, which they want to build the supercomputer, which will have the 100 times more powerful than this supercomputer in 2030. So they aim to take the top spot in the supercomputer in 2030. And then that is the spot for the second, right now, the second ranked supercomputer, but which was the top supercomputer a few years ago. And that is in the Department of Defense, Oak Ridge National Laboratory in US. And this has actually the so-called 1.353 flops. And this is the first computer to exceed or hit the exaflop test. So to give you the context, so it would take the entire population of the Earth more than 4 years to solve what frontiers can solve in 1 second. Right? So it has more than 9 million. So that is equivalent to about 1 million, more than 1 million desktop computers. So this is huge, huge supercomputers. And the today's top supercomputer is El Capitan, which is also located in US and owned by Lawrence Livermore National Laboratory, and which has more than 11 million CPU cores. So which is it's amazing. So the power of numerical computation is actually huge because it has numerous applications. For example, we can apply this regional and global seismology, tsunami simulation, landslides, mining, weather prediction, and a lot of applications. And today, I will demonstrate the use of the power of numerical computation for the soundscape application. So, of course, we need to solve the math equation. So that is, I'll just briefly do not go in detail about math, but just for some technical reason, I have listed here. So we need to solve so-called two equations, elastomodynamic equation and acoustic equation. So it is basically, if you have heard about the Newton's second law of motion, basically that's it, Newton's second law of motion in the solid and fluid medium. So we apply the force and compute the pressure or displacement depending on the solid or fluid. So the analytical solution of this problem is very difficult. So that's why we need the numerical technique. So we have developed the spectral element method. So we have developed several software based on this. So basically, it uses the very high resolution element. So if you see that element, so it has the number of nodes within that element, and on the right you see the polynomial plotting. So it is very high degree polynomial to approximate those variables, and basically it makes the so-called mass matrix diagonal, which makes the time matching scheme very, very efficient. So that is the reason why we use this method. So and there are several softwares that we have developed which are open source and publicly available through the specfm.org. And these are adapted to the modern GPU clusters and can be used to several problems, even the medical imaging. So before going into the soundscape in the city of Kingston, I wanted to show you the interesting complex model that we can solve using the numerical model. So this is the very complex model. So you may be wondering why this is the complex model. So if I change that picture into the velocity or some elastic properties, it would like this. So you will see the very highly variable material properties in this picture, right? So that's why it is very, very complex model. So that dot on the forehead, so I put the source there. So you can imagine like I'm meditating or something, so creating some energy. So I want to see how the wave would propagate in this complex model. So first we need to actually decompose that into the simple geometrical structure. So that picture is now decomposed into the quadrilateral like this, right? So to represent those complexities of that model. So after that, so here, so I will show you how the wave would propagate if I have the source or some noise or whatever in my forehead, right? So as you can see, that this is the wave propagation through there. So because it's the very complex model, you can already see rooted wavefronts and very, very complex wave field, right? So that is the power of numerical solution. So we can use this numerical solution to simulate the very complex model like this one. So now let me describe how we compute the soundscape in Kingston. So this is the region of Kingston. So my home is somewhere in this side, so it's not shown here. We wanted to focus in near the train station. So this is the Kingston train station, and these are the some commercial complex and the some residential complex. But initially, due to the limited computing power in our lab, we just wanted to focus in this region. At how for example, the noise or the sound when the from the train when it blows horn when it's stopping at that train station would propagate through that region. So the Kingston is relatively flat. So in the color map, you see the elevation. So it varies from 74 to 140 meters. So it's relatively flat. So these white blocks are the building extracted from the GIS. So, and we'll focus our modeling for this train station. So here we just included two suburban developments and two commercial zones. It was relatively flat, so we didn't consider the three-dimensional model. So this model would look like this. So it represents all the residential block somewhere here. So this is the train path on the middle. So this is the train station. So we are basically covering about the 2.2 kilometer times 2.5 kilometer region. So again, we need to decompose that into the simpler geometrical structure, which would look like this. So this simple geometrical structure, the quadrilateral, would honor all those corners of the building and those land and area. So the element size in this case varies from 0.1 meter to 2.2 meter. So that variation is due to the fact that we have very complex geometry. So we need to adjust the mesh size to accommodate all the complexity. So total elements in this model are about 5.6 million. So this is the interesting result. So you will see in this movie how the sound from the train horn will propagate and how that will interact with let me put this again. Yeah. So now as you see that the sound is propagating like this, and it hits the boundary of the buildings or building, but it is reflecting back, right? So you can see there's a lot of reflection and a lot of that refraction and so on, and they combine again together and produce the very complex noise map here. But as you can see, for example, in this region, it is very less sound due to the observation from the building, and in some area is high noise like that. So that is the noise interaction. So let me play that movie again, right? So it's again propagating that sound from the train station, and then it is propagating throughout that area. So it hits building, and they observe some sound as reflects back, and they again interact with other reflected or directly traveling waves, and they build or generate the complex noise map. Right? So this is the one typical noise map due to the train horn when the train is moving towards the train station. So now in acoustic field, they compute so-called maximum sound pressure level and the equivalent continuous sound level. So here you can see on the left is the maximum sound pressure level. So that is basically during the that time period of the train or blowing. So if you go to some space, that color bar, color scale basically represents the maximum pressure at that region. And on the right is the equivalent continuous sound level there, right? So as you can see that this map is very, very complex. It's primarily due to the presence of the building and that sound or the noise interact in a complex manner with this building. And now we are able to reproduce this complex behavior using the numerical computation. So in the next, this is very interesting comparison between the stationary source, also the moving source. So on the top, you will see the result for the stationary source. That means the train is not moving, but it is still blowing the horn. On the bottom, you will see the result for the moving train. So the train is blowing the horn while it is moving. So the result is very, very interesting. So as you can see in the top, for example, on the left, you will see the circular wavefront, right? Because the source was stationary. But when it interacts with the building structure, then it produces the complex sound map, right? So But on the bottom, so you can see that because the train is moving, the propagation is no longer circular, even in the absence of building, but it even produces the more complex picture of the sound map when the train is moving. So that's why the considering the movement of the train, for example, traffic and so on, is also critical to produce the realistic soundscape for devices. So this is another interesting comparison. So left is the homogeneous. So that means assuming that there are no building. So it's just the air. And on the right, there is building. So as you can see that, so this straight line is where we plot this graph on the bottom. So blue is for the homogeneous model, and that red is the heterogeneous model. As you can see from this graph, the picture for the heterogeneous is very, very complex. And that is due to the presence of the building structure or the infrastructure. So as it's also evident from this picture that that's why the considering the complex urban environment is very, very important to reproduce or predict the realistic soundscape for the device. So now I'll show you another interesting competition that my student Pedro Lapierre did. So which is the sound propagation or the noise propagation or the noise map due to the church bell, right? So the church, they ring the bell every hour, and you can also hear this from the very far. So this is very famous church in Kingston. It's near our university, St. Mary Cathedral. So I'll just play with this sound. I think you are hearing this. So it plays that every year, right? So you can hear the sound in several kilometers from this church. And we're interested how that sound propagate and affect the noise map. So the right is the area where we consider Ford Morley. So this is the area. So this the yellow area, and we initially just started with that darker yellow region, and then expanded that to the lighter yellow region. So the process here is that first we extract that model in the GIS. So it looks like this, and then we build the 3D model like this. So in the previous trend model, you saw the result of the two-dimensional computation, which is usually cheaper in the computation cost, but this is significantly higher computation cost. So we build the 3D model like this. And these are the results. So this ball-like structure is basically the level of sound or the wavefront of the sound pressure, sound level. So in the first, you will see this sound pressure. So because it is closer to the source, you see the darker color. So it has the highest intensity, and it as propagates. So its intensity will of course decrease, but it will interact in a very, very complex manner. Right? So it propagates, you will see a lot of reflection or refraction throughout the building and these open spaces, and they interact in a complex manner, and they produce the noise map or the map this. So this is another picture that my student produced. So he basically analyzed those results for the different frequencies, and you can see the very complex picture here. Right? You can even kind of trace how the noise or the sound would propagate through those open spaces like this to produce the complex sound map. So like this, right? So they are repeating from multiple buildings, and they are interacting again, combining together. Sometimes they cancel out, sometimes they actually add up. So that's why, depending on the place, somewhere it could be a little bit quiet, and somewhere it could be louder, and so on. So that means with the numerical computation, we can actually produce this kind of the complex noise map for this model, even for the 3D model. And then this is the noise map for that case. So this left is the maximum pressure level and or the sound level. On the right is the equivalent sound or equivalent pressure level. Right. So again, you can see in this case the torch bell. The torch is not moving. Right. It's the stationary source. So that's why in open space near the torch you see the circular projection of the sound level, or the similar to the pen sound. But again, due to the presence of this building structure, you would see the very complex interaction of the sound level, right? For example, in this area, it's blocked by those buildings and so on. You will see this seems to be the tightest area in this region, right? But the near the south, it's the high intensity, and these open spaces, we have the high intensity level. And you will see from this three-dimensional computation, we are now able to reduce or predict this soundscape for the complex urban environment. So finally, I'll summarize our. So now we're able to compute the high resolution noise map in complex urban environment in real world scenario. So as you can see from these videos, that you can see the very complex noise dynamics, and our simulation is able to capture those complex behavior, right? How the noise or sound interact with city still infrastructure. Then, when this gives us the kind of the clear or the deeper picture or deeper understanding of the urban, how they interplay with the infrastructure or how they interplay in the complex environment. And finally, this will be very helpful tool for the planning application. For example, let's say if we want to build a new infrastructure, we can do this computation in advance, and we can see how that will perturb or disturb the existing soundscape in the area. Right? So that will help us to mitigate the noise pollution and also to make the informed urban design planning in future. So yeah, those are this concludes my talk. So if you have any questions, I'd be happy to answer. Thank you.
Okay. Thank you, Dr. Garthis, for such a wonderful and very thought-provoking ideas here. It's really tough for many of us because we are from non-technical background, this engineering background. I have so many questions in my mind, though. So I'm
Yes, of course.
going
Please,
to see
please.
other questions. So first
Yeah.
question. Let me begin from my question, and then I'll read other question.
Yeah.
For those of us like me, coming
Yep.
from an engineering background,
Mhm.
could you please briefly explain in 3 minutes, 2 minutes, 1 minute, something like that, what makes this spectral element method particularly suitable for modeling urban soundscapes compared to other numerical approach, number one. Number two, what is this
Yeah.
idea essentially in a very simple layman's language, instead of, without showing any
Yeah. Yeah.
picture, any graphics, anything. Simply, what is soundscapes? Why it is important? First of all, number one is this, and number second is the second question. Okay, go ahead for that, and then I'm receiving here some question from the participants.
Yes. Yes. Yeah. Thanks for this interesting question. So yeah, of course, I understood this could be a little bit complex because it's a kind of highly technical. But yeah, of course, the
You can stop
soundscape.
sharing if you want to.
Yeah. Yeah. So as I said in the first slide, so the soundscape is very similar to landscape. In the
Landscape.
landscape, we see the kind of the land forms and trends and so on, right? And in soundscape, we see the similar feature of the sound,
Hmm.
right? So you could prepare that. Of course, you cannot see that with your naked eye, but we can present that so that we can see it, right? So basically, kind of characterizing the sound to map that sound level in that's a landscape or certain region, right? So basically, the soundscape gives you the level of sound or the noise in particular location.
Okay, so one more
And the
question.
second question,
Go ahead.
another question was why spectral-element method is uh, advantageous, right, over the other method. There are several methods, for example, finite difference or finite element and so on. But the spectral element method is actually a higher order finite element method. So it is very kind of advantageous when we want to represent or build the model, which are very, very complex, which is the case for the urban environment, because there are different kind of building structure. Sometimes it could be some topography, complex geometry structure. So it is actually kind of easy to represent that with this. And also it gives, if we want to produce the high resolution, high accurate map, so spectral-element method is the method to choose for this kind of problem.
All right. Okay. Thank you. So at least we can grasp some idea on this.
Yeah,
So
yeah.
Professor Basu Sharma and Dr. Sandaman Rai have posed some questions here. So may I request both of you can open your video and can explain your question yourself so that the discussion can be rigorous. Anybody can begin. Okay.
Oh yeah, yeah, yeah. That's a great idea. Yeah.
Okay. Go ahead, sir.
Yeah, actually, it is not a question. This is basically thank you. It's such a very complex and very important noise behavior. You presented in such a lucid way. Even a very lay person like me, for understanding a topic like this, you could understand part of it at least. And thank you very much. So
Thank you,
very good.
Basis.
Thank you, Basu sir. It's a very definitely very appreciated, very difficult, very the whole simulation, whatever he has done to prepare this presentation, it takes more than a week to prepare just for the presentation. Dr. Sandaman, sir, go ahead with your question.
Uh, Hello everyone. Thank you, Omna sir, for your nice presentation with very complex modeling. I'm also very far from your modeling. I have a question because it's very nice presentation, especially sound propagation in the urbanization area. So I have posted a question because it's very interesting because normally in the daytime it's very noisy, lot of vehicles and people, a lot of activity during the daytime,
Yeah,
but in
yeah.
night time it's very quiet. So how you collect the information and put in the modeling? Is there any you'll see the difference in the modeling during the daytime or nighttime? Certainly it
Yeah,
should be,
that
but I
yeah.
don't know. Thank
No,
you.
no, no. That is great question actually. Yes, that is great. With, for example, that's exactly right. For example, during the day, so I live about 7 kilometers from the train station. So I don't usually hear the train sound. I think I hear it, but because there are other noises also, right? So that's why I do not give attention to that particular noise from the train horn. But during the night when I'm sleeping, sometimes suddenly in the midnight I hear the horn, right? So that's of course the one thing is because there are no other sound sources. So usually it is not attenuated, not interacted. So it's usually the sound intensity is higher. And another thing is of course the temperature. So the due to the temperature, so the sound speed is actually differs. So during daytime, in the nighttime, sound speed will be different, and that will affect the intensity. And in fact, we actually have done that both observation and the modeling of that, and there is of course the difference. And the right now, so the next the future work is to include the traffic also, and that will give also the more realistic or more effective picture, right? Because during the night there is a less traffic, and during the day there are traffic. That's very interesting question. Thank you.
Yeah, thank you very much. I want to ask another question in the
Yes,
meantime.
of course, of
So,
course.
I don't know. That's why I'm going to ask you because when we develop very sophisticated computer or mobile, day by day or even in coming days, do scientists use the modeling all the time to improve the quality or new advanced computer or any technology? All the time they use the numerical model, to
Yeah,
develop any
yeah,
new kind of
yeah,
invention.
yeah, exactly. Because the big advantage of the numerical modeling is it is non-destructive testing, right? For example, let's say if we want to check whether the buildings is safe or not, then maybe you could test with this some Smith hammer or something that could be destructive, right? So it could maybe destroy or made some damage to the building. But with the numerical modeling, so of course we need to properly use those material and so on. So that means you can do many times, right? So destructive testing you can do only maybe once or so. You can do many times until you actually improve the result, right? For example, let's say when they send the rocket to the Mars or Moon, they even do the numerical simulation
Mhm.
several times, thousand times, to make sure that every parameter is correct it will sustain, it will not have the damage and so on, right? So that's why numerical modeling is very, very powerful tool. So I mean, without numerical modeling, humanity would not develop so far for sure, I think.
Thank
All
you
right,
very much.
thank you.
Thank you.
Thank you
Excellent.
so much,
Thank you.
Dr. Subban, sir, because he is from the similar background and he knows more because he is a geological expert. We have two hands raised here, Archan Dawardi and Subhas Podal. So let's go with Archan Dawardi and then Rabindra Chamlaganji, I think. So let's go with Archan Dawardi first, then Subhasji second, then Ravindraji third. You can unmute yourself when speaking, and if you want to open your video, you can open that too because I have allowed it. Please go ahead. Archanji first, then Subhasji, then Ravindraji.
Sir, namaskar. I'm Archan Dabari. I work for Canadian Armed Forces, and I am also kind of responsible for integrating new technologies into our operations, things like that. So,
Very interesting.
yeah, and I found I have worked into like in the application side of it. I worked with the sound a little bit because
Yeah.
I did some geophysical surveys in underwater and overland in Nova Scotia
Mhm.
for a couple of years. So I kind of very much interested in this as well. So just a couple of questions I have. Sorry, I'll take up some of your time. So first question is like on top of Santaman Rice's questions. So there are other sources of noises in the area as well, right? While considering these urban design. So I was just wondering, how do you consider like can you simulate? Can you ingest more sources of noises in the tool that you were using right there? And can you do that? Was my first question, right?
Exactly that. That's very interesting question. And just for your information, we actually work with the Canadian Forces,
Okay.
Department of Defense,
Yeah.
and we have the project for the drone sound modeling.
Okay.
Yeah,
Okay.
with
So
the
I will.
ideas project.
Yeah.
But to answer your question, I think we should include that.
Yes, I think we
Yeah,
should chat on a separate. Yeah, we should do that separately.
yeah,
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 that sounds
yeah,
good.
yeah. So yeah, for your questions, that's very interesting. And yes, we can definitely include the other sources, traffic. Maybe there are some industry complex or an machinery or even the crowd and so on. So we also did the modeling of the concert. So yeah,
Yeah.
that's definitely possible. So the next task is actually we are working with the proposal with the EH3 right now for the Alliance project.
Okay.
So our project proposal involves the bigger urban area. So we are considering the Toronto or Vancouver, and
Yes.
then include all sound sources, traffic, industrial complex, and so on.
Wow. Awesome. Awesome. Sounds great. Looking forward to hear more on that.
That's absolutely
More.
awesome.
I got more questions if you don't mind, please.
Of
Because
course,
this is
of course.
such an interesting topic for me. Uh, so what tool was used to create the sound propagation map of Kingston, the train station that you showed us? Like, was it the tools that you showed us, the open source tools that are available?
Yes, yes, exactly. So
Awesome.
that we developed them ourselves,
Yeah.
and it's the that consortium involved the international partner. Yeah,
Yes.
so it's both two-dimensional, three-dimensional, and we even have the software for the geotechnical engineering. That we use that software.
Awesome. Okay. And the videos we saw today are all simulations, right?
Yes,
Okay.
yes,
Okay. These are okay. Cool. Sounds great. And last question: if your presentation
of
can be
course, of
emailed
course.
to us, please.
Yes, of course, yes.
Okay.
So I don't have your email, but I'll find it out.
Yes, sir. I'll just put my email address on the chat here as well.
Oh, that would be good. That would be good.
Awesome. Okay.
Yeah,
Thank you
that
so
would
much, sir. It was such a wonderful presentation, and
Archan.
I'll look forward to talk to you again.
Thank you very much. Yes, me too.
Thank you,
So
Archanji,
I
for
have one question on the chat.
yeah,
Yes.
yeah.
Um,
Before going to chat question, there are two people waiting
okay,
first,
okay, okay. Yeah.
Podalji and Ravindra
Oh yeah,
Sharma
yeah,
will be
yeah.
there. And in the chat box, Manishji has posed a question.
Yeah.
Santosh, Bina Sharma, and Ambikaji, they simply appreciate it. So let's go with Subhasji and Ravindraji, and then we go with the question from Manish, and now I see some message from Keshav Sharma as well. Okay, go ahead, Subhashi.
Thank you, Humna sir, for your nice presentation. If the folks know, he's my teacher of my bachelor's degree 25 years back. Yeah, the question is, like, I don't live nearby the railway station, but I live nearby the aerospace, the airport, Ottawa airport. So how is the model would be different in comparison to the sound we propagate from the land versus that comes from the aerospace thing? Just curious to know.
Yeah, no, that's very interesting. Actually, we have already done that simulation regarding the drone. So yeah, it's in that case, it's very different because in the air it's kind of homogeneous, but there are air layer depending on pressure and temperature variation. You will not see that complex on the air itself, but when that sound arrives and hit the ground and building, then it will have the very complex interaction like what we saw today.
Thank you.
All right. Next question goes from Ravindra Cholagai, Dr. Ravindra Cholagai. He's a professor here in the, I don't know which university, I forgot the name, but it's the eastern part of Canada. Okay, go ahead, Ravindra, Dr. Ravindra Cholagai. Yes, please.
Thank you so much, Manu sir. I have actually I have no question at all to ask. But like it's really interesting. I didn't understand anything else because I'm completely somebody else working in different areas of research and studies, as Professor Basu Sharma said. One of the things I found quite interesting to learn by listening to you today, Home Nazi, is that like if somebody else were there, like with social sciences background, discussing about all those things like urbanization and urban thing, and it would definitely be a focus on capitalism and neoliberalism. Like they would be like basically like a new terminology for the social, like natural scientists as well. So I did understand that way, how complex world is this we have been living in. And just I have no question. I wanna say that thank you so much for sharing your great research. It's really honor to be a part of this talk today. Thank you so much.
Thank you, Amansi. And actually, yeah, so it's very interesting comment. And actually, there are some recent research emerging where they actually kind of experiment with this some sound, because there are some sound which actually are pleasing for our brain, but some sounds which are actually irritating for our brain, right? So there are some experiment where they play this pleasing sound and they see how that affect our mental mood. Or for example, even the growth of the some plants or something. So we could do this modeling also, which is very, very amazing.
Yeah, just like making a quick note, like to Banushers. Yeah, I teach in a very small university. Maybe it's not well known. That's why you didn't know.
No. I just forgot the name. Sorry. It's not bad.
Yeah, I teach at Acadia University,
Acadia
which is one of the oldest.
Of course, I know that.
One of the oldest universities in Canada, even though it's very small and in a rural area. That's your research also very much aligned with the idea. Like I'm located in very urban, like very rural areas of Nova Scotia, this is the valley. So yeah, okay, yeah.
Let's be in touch.
Yeah, thank you, Raminderji. It's just great to see you having this discussion. And here are Manishji's question: how was the heterogeneous model validated against real-world measurement of high fidelity simulation? Manish, do you want to explain further?
Yeah, sure. So nice talk, Dr. Home. So I could relate a lot of things, although I don't belong to this field, but but I'm expert in cancer, landscape, mutational landscape. So I know like what are these heterogeneous and homogeneous model, because we have to do a lot of those things. So my question was like, how, was this heterogeneous model could be validated against real world measurements or high fidelity simulations?
Yeah, Manish, just out of this talk. So actually, we are doing the cancer simulation as well.
Oh,
So
okay.
the diffusion reaction model, how the certain medication would affect the cancer cell and so on and growth.
Oh,
So I
okay.
think we should talk about that.
Yeah,
But
yeah,
to
sure.
your question, that is very interesting question actually.
Uh-huh.
And in fact, what we did is we recorded the sound when it was blowing on or the playing that torch bell. We
Mm-hmm.
had the microphone, ambisonic microphone, and then we recorded them in real, right? And then we model it. So of course, we the when we benchmark, so we compare the principal features and measure
Mm-hmm.
amplitude, and they were very very good.
Mm,
Yeah,
okay.
so yeah, that is possible because we can buy this microphone. They are very cheap, and we could observe anytime. But my student had to go to the quiet time. At Santaman said that the daytime and is different. So he went there early in the morning when there was not a lot of traffic and so on. That's how we benchmark.
Oh, okay. So I have another question, if you don't mind.
Yeah, of course, of course.
Yeah, yeah, sure. So, how robust, are these results that goes across different environments or cities?
Oh, they are very, very robust. So
Oh,
only
okay.
thing is that if we go to the different environment, then
Uh-huh.
we need to build the model from the scratch.
Okay.
But the numerical tool is still the same.
Oh,
So that's why our long-term vision is also that the some sort of AI modeling. So we
uh-huh.
could build this model using different kind of region
Uh-huh.
or building a fictitious model and so on, and train the model and then generate this kind of map using AI. That is the long-term vision.
Oh, okay. Yeah, by the way, nice presentation, all those graphics and then
Thank you. Thank
everything.
you.
It was quite interesting. So, yeah.
Thank you, Manish. And you can definitely relate because he has cancer simulation as well.
Yeah,
So,
yeah, exactly.
okay. So it's a great thing. So here are some more comments are coming, and Anmika Podel, one of the Can4 family members. So she's asking some question. Anmika, can you come up and explain your question yourself, or we just read it out? Yeah, she's here.
I can
Yeah,
explain.
welcome.
Sorry. Thank you so much, Omnath sir. This is, I'm also new to this area and I found very, informative and interesting the way how you started comparing soundscape with landscape and the circle with segment. I really like that. So my question is
Thank you,
more
Angie.
rather than question is I'm curious to know about the policy implication of research like this.
Yeah.
It's related to urban infrastructure planning, train noise, and then so how the finding of such research can impact the decision making for urban infrastructure planning, and have you already seen
Yeah.
some sort of this evidence-based decision in country like Canada, like developed country? I just want to know
Yeah.
more about
That's a
that.
great question. For example, in organized the European Union, in some city, they actually developed this urban soundscape to facilitate this kind of design or mitigation. So our ultimate goal is to make kind of the open database. For example, let's say
Great.
if public is interested, they could just go to that website and see what is the noise level in that area, right? For example, let's say if
Wow.
somebody is had the hearing problem, they choose not to go in that area. For the policymaker, for example, they could, let's say, place the building or let's say train station somewhere there, and they could immediately see how that will affect the existing soundscape. For example, in that, let's say, negatively affect the area which is densely populated, then they will consider moving to the different place, right? So something like that. That is our kind of the ambitious idea.
Wow, great. Like it's can be related to many things, health and as
Yeah.
well as like, and I found very interesting that 3D versus 2D kind of thing. And have you
Yeah.
already tried the comparison, different model using that
Yeah.
approach?
For the church, yes, we compared the 2D and 3D. So the general features are very similar, but some of the detailed feature will be different due to the 3D interaction.
Okay. Thank you. Thank you so much.
All right. Okay. Thank you for the question, Amikaji. Because everybody is so much interested. Basu sir already thanked and Santamanji already questioned. Beena Sharma, she wrote just very interesting. Santosh Upadhyay, he also said, thank you very much for this interesting presentation. Manishji asked the question himself. Amikaji asked herself question. Keshav Sharmaji is writing here, great presentation. Just curious, did your modeling account for variations in building typology and geometry, moving vehicles and roads and vegetation? And how did these factors influence sound propagation in the urban environment? Yeah.
Well, that is a great question. Thank you, Dr. Keshav Sharmaji. So yes, we consider the geometry of the 3D model, but we did not consider the typology of the building at this time. And the vegetation is also very important, as you mentioned there. We have not yet included that. So, but the vegetation will be critical, how it attenuates the sound through the media. So those are actually in the planning for the future. So that's a great question.
All right. So thank you, Dr. Sharma, for the question again. Arsan Dawadi already asked a question. Govinda Dahal, Dr. Govinda Dahal, he said, thank you, Homnaji, for the great presentation. It needs a lot of efforts. It has a huge potential to explore further on the physical and mental health due to the sound pollution. Much appreciation for this research. And Mayuri goes from India. She is the only participant from India, I believe, today. It's a good evening to everyone. So because India has an evening time now, though I'm not from this field, it was completely new for me, but I really enjoyed the session by learning something new. Thank you so much. Thank you, Mayuri. It's a good to see you here. And Subhashji already said this recording will be on the Can4 webinar 2 series, and there will be a YouTube. So later on, so if you want to watch this video, this discussion, you can see. And here, Subha Gautam, Dr. Subhari Gautam, he is saying, great presentation, Homji, very intriguing. I need to leave now, but wish everyone a nice weekend and happy holidays. And Ravindraji also thanked here. And Gyan Saipon, so I'm not sure who exactly the name. Thank you, Homnaji, for this great presentation.
Yeah.
So finally, everybody almost tried to respond you and ask so many interesting questions. I don't have any further question, but if the soundscape was in Kathmandu, for example, if you have to plan soundscape in Kathmandu, because Kathmandu is a valley, a lot of crowd, a lot of noise, no planning. So what is your good tips for one or two, three tips, something, and then we will wrap it up.
Yeah, no, that's a great question. So when I was presenting on when I was working on this topic, so Kathmandu was in the first. It was first on my mind actually because I, of course, spent several years there for my undergrad degree. So yes, I mean we could do this kind of modeling there as well because the GIS map we can easily access it. And then using traffic and so on, yeah, we could do this modeling. I'm actually thinking to collaborate with my previous student who is an environmental specialist about this actually.
Okay. And Saligramji is thanking here with some words. Thank you, Dr. Garthi, for excellent presentation. Enjoyed listening to you. And now we are coming to the closing. As we conclude today's webinar, I would like to sincerely thank Dr. Homnath Garthi for sharing this research and expertise with us. And I thank all participants for joining and contributing to this session and asking questions and making this discussion more lively and engaging. Canfor will continue to organize similar research-focused events, webinars in coming months, and we encourage you to stay connected with us. Hopefully, during the reading weeks of February, we'll organize another seminar. Once again, thank you for everyone for your time and participation. Have a wonderful rest of the day and happy holidays. They are coming. Thank you.
Thank you, everyone.
Thanks.
Let's end the session here.